In the event of general war in Europe, the speed at which the Soviet Union and its Warsaw Pact allies could mobilize and concentrate forces westward would determine whether strategic surprise translated into operational breakthrough. And by the early 1950s, Soviet military planners understood that armored divisions, artillery groupings, missile brigades, and logistical echelons could not reach forward assembly areas by road alone, because the sheer mass of modern mechanized armies required rail transport measured in thousands of wagons per day, leading to the systematic design of a rail-based mobilization architecture stretching from deep within the Soviet interior, through Poland, Czechoslovakia, East Germany, Hungary, and beyond, structured not merely as a civilian transport grid, but as an integrated military instrument calibrated for rapid concentration along NATO's central front. And this architecture drew directly from Second World War experience, in which the Red Army had relied on rail corridors to shift armies across vast distances, lessons institutionalized within the Soviet Ministry of Railways and the General Staff, which jointly developed detailed mobilization timetables, specifying how many train sets would be required to move a tank division, how long loading would take at designated embarkation stations, and how many parallel tracks were necessary to prevent bottlenecks under surge conditions. And as the Warsaw Pact was formally established in 1955, the alliance inherited not only political alignment, but a strategic requirement to harmonize rail infrastructure standards across multiple sovereign states, including track gauge compatibility, axle load capacity, bridge reinforcement, and signaling systems capable of sustaining dense military traffic, particularly along key corridors linking Soviet territory through Belarus and Ukraine into Poland and onward toward the inner German border. And because the Soviet rail gauge differed from the standard gauge used in much of Central Europe, planners developed transshipment hubs near border regions where rolling stock could be exchanged or cargo transferred, while in certain areas broad gauge extensions were pushed westward to reduce delay, reflecting a deliberate effort to compress mobilization timelines measured in days. And by the late 1950s, Soviet operational planning assumed that in a crisis, forces stationed in the western military districts would begin immediate movement toward pre-planned concentration areas, with follow-on echelons arriving from interior districts via prioritized rail corridors. Each corridor mapped and classified war plans that assigned daily train quotas and established traffic control headquarters responsible for sequencing departures and arrivals to avoid congestion. And these quotas were calculated against measurable capacity, such as trains per hour per track, average wagon load in tons, and turnaround time at unloading ramps, because mobilization efficiency depended on precise synchronization rather than improvisation, and infrastructure investment reflected this priority, with extensive double tracking of main lines, construction of bypass routes around major cities to prevent civilian congestion from interfering with military movement, reinforcement of bridges to support heavy armored loads, and expansion of marshalling yards capable of assembling long military trains composed of flat cars carrying tanks, boxcars carrying ammunition, and tankers carrying fuel. And throughout the 1960s and 1970s, Warsaw Pact exercises such as Zapad and Soyuz repeatedly tested these rail mobilization procedures, rehearsing the loading of divisions onto rail cars within specified time windows and simulating the dispatch of successive echelons westward under conditions of assumed NATO air interdiction, prompting the development of camouflage techniques for trains, dispersal of rolling stock in peacetime to reduce vulnerability, and the prepositioning of repair battalions tasked with restoring damaged track segments, because Soviet doctrine anticipated that NATO air forces would attempt to disrupt rail lines in the early stages of war, and thus resilience required redundancy, including parallel routes and pre-planned detours capable of absorbing diverted traffic without collapsing the overall flow rate. And by the 1970s, the rail network serving the Warsaw Pact's Western Theater had evolved into a layered system in which civilian freight lines doubled as mobilization arteries, governed by centralized dispatch authorities in Moscow, coordinating with Allied ministries in Warsaw, Prague, and East Berlin, ensuring that in the event of activation, civilian passenger services could be curtailed and freight priorities shifted immediately to military traffic. A transition rehearsed during readiness drills that measured how quickly schedules could be cleared, and tracks reserved exclusively for troop and equipment movement and intelligence. Assessments produced by NATO throughout this period consistently identified Warsaw Pact rail density as a key enabler of rapid force concentration, noting that the proximity of railheads to forward garrisons in East Germany allowed armored units to move from peacetime bases to attack positions within compressed timelines, potentially achieving numerical superiority before NATO reinforcements could arrive from across the Atlantic. And this assessment was grounded in observable infrastructure metrics, including the number of parallel east-west trunk lines feeding the German Democratic Republic, the capacity of bridges over the Vistula and Oder rivers, and the scale of freight yards in cities such as Brest, Poznan, and Dresden, each capable of processing hundreds of wagons per day. And as Soviet operational art matured with emphasis on deep operations and operational maneuver groups in the late 1970s and early 1980s, rail mobility became even more central because the rapid introduction of follow-on forces to exploit breakthroughs required reliable rear area transport able to sustain continuous waves of movement, with planning documents estimating that a single tank division required dozens of trains for complete relocation, each train occupying track space and signaling intervals that had to be carefully managed to prevent gridlock, and therefore rail capacity planning extended beyond track length to include signaling modernization, installation of automatic block systems, and the expansion of locomotive fleets capable of hauling heavy military loads across long distances without refueling delay, while fuel depots and maintenance facilities were positioned along key corridors to sustain rolling stock under high-tempo conditions. And by the early 1980s, the cumulative result was a rail mobilization network stretching thousands of kilometers from the Urals to the Elbe, engineered to translate strategic warning into operational mass within a matter of days, forming the logistical backbone of Warsaw Pact war planning and shaping NATO's own defensive calculations about reaction time and forward deployment. By the mid-1960s, the Warsaw Pact rail mobilization system had evolved beyond a collection of reinforced trunk lines into a centrally orchestrated operational instrument governed by detailed timetables embedded within classified mobilization plans, because Soviet General Staff doctrine required that force concentration along the Western theater of military operations occur in sequential echelons, each echelon assigned specific rail corridors, loading stations, and arrival windows designed to prevent congestion while maximizing forward mass. And these timetables were calculated with mathematical precision, estimating average train length in meters, axle load in tons, and track occupancy intervals measured in minutes between successive departures, ensuring that under surge conditions, main east-west corridors could sustain a dense stream of military traffic without degrading signaling safety margins. And this level of planning demanded infrastructure reinforcement across Allied states, including the expansion of double and triple tracking in Poland and Czechoslovakia, the strengthening of river crossings over the Vistula, Oder, and Elbe to accommodate heavy flat cars carrying main battle tanks such as the T-62 and later the T-72, and the modernization of marshalling yards near key nodes like Brest, where transshipment between Soviet broad gauge and European standard gauge systems required rapid exchange of rolling stock, accomplished through prepositioned cranes, adjustable bogie systems, and dedicated transfer ramps capable of processing entire battalions within defined loading cycles. And because Soviet planners anticipated that NATO air forces would attempt to interdict choke points early in a conflict, bypass lines were constructed around major urban centers, tunnels were reinforced, and alternative routes mapped in. Operational plans so that traffic could be rerouted without collapsing the overall flow rate, reflecting a design philosophy centered on redundancy rather than single corridor reliance. And throughout the 1970s, Warsaw Pact exercises increasingly emphasized speed benchmarks, measuring the time required to load a motor rifle division onto rail cars from garrison, often targeting completion within 24 to 48 hours, followed by transit times calculated against locomotive horsepower, gradient profiles, and refueling intervals, because the objective was not merely movement, but synchronized arrival at forward assembly areas in East Germany and Western Poland, where units would detrain at designated ramps positioned near highway networks leading to the inner German border. And these ramps were constructed with reinforced concrete aprons and multiple sidings to permit simultaneous unloading of tanks, infantry fighting vehicles, artillery pieces, and support trucks, minimizing bottlenecks during the critical transition from rail to road. And as Warsaw Pact doctrine incorporated the concept of operational maneuver groups in the late 1970s, which envisioned rapid exploitation deep into NATO territory following initial breakthroughs, rail capacity calculations were adjusted to account for the need to sustain successive waves of reinforcement beyond the first echelon, including reserve armies drawn from interior military districts, thereby expanding the scale of projected rail traffic to levels requiring near continuous occupation of main lines during initial conflict phases. And locomotive fleets were expanded accordingly, with heavy electric and diesel units assigned priority status under mobilization codes that preempted civilian freight schedules, while centralized dispatch authorities coordinated movements across national borders under unified command arrangements that allowed Moscow to issue traffic directives overriding local civilian priorities. And intelligence collected by NATO during this period consistently assessed that Warsaw Pact rail density in the Western theater exceeded that available to NATO for equivalent east-west movement, particularly given the alliance's dependence on maritime reinforcement and the relative scarcity of parallel rail corridors feeding the Central Front from Western Europe, reinforcing Western concern that the Pact could achieve local superiority in the opening days of war by exploiting its integrated rail mobilization grid, and by the early 1980s, signaling modernization programs introduced automated block systems and centralized traffic control in key sectors, reducing human dispatch delay and increasing permissible train frequency per hour, thereby enhancing throughput under wartime conditions, while maintenance battalions equipped with track-laying machinery and portable bridging equipment were assigned to follow major echelons to restore damaged segments rapidly in the event of interdiction, demonstrating a comprehensive approach that integrated engineering, rolling stock logistics, and operational doctrine into a single mobilization framework. And across the vast geography from the Western Soviet Union through Poland into East Germany, the rail network functioned as the primary artery through which divisions, missile units, fuel tankers, and ammunition convoys would flow in compressed timeframes, embodying a logistical design intended to convert strategic warning into immediate forward concentration, and by structuring the system around measurable capacity targets in trains per day, tonnage per corridor, and unloading time per division, Warsaw Pact planners sought to eliminate uncertainty in the most critical variable of continental warfare, the speed with which mass could be delivered to the decisive point, thereby shaping the strategic balance in Europe throughout the height of the Cold War. As Warsaw Pact operational planning matured during the late 1970s and early 1980s, the rail network was no longer treated merely as a transport utility, but as a calibrated mobilization engine synchronized with the phased structure of Soviet offensive doctrine. Because general staff concepts divided wartime operations into successive echelons whose movement schedules were pre-written into mobilization directives, assigning precise departure windows to specific military districts and allocating defined track capacity along predetermined corridors. And these allocations were grounded in empirical studies of line saturation, calculating how many military trains could traverse a single double-tracked main line within 24 hours without exceeding safe headway intervals, often targeting sustained densities of dozens of trains per direction per day under surge conditions, while factoring in locomotive turnaround cycles, crew rotation, refueling points, and the availability of passing loops to allow overtaking of slower freight, ensuring that heavy armored trains carrying tanks and self-propelled artillery could maintain predictable transit times, despite gradient variations and seasonal weather effects. And to support this tempo, the Warsaw Pact invested heavily in marshalling yard expansion, constructing classification yards with multiple parallel tracks capable of assembling complete divisional train sets, each composed of flat cars rated for axle loads exceeding 60 tons to accommodate main battle tanks, boxcars for ammunition secured under strict handling protocols, and tanker wagons for fuel. And these yards were positioned strategically near major junctions such as Brest, Warsaw, and Frankfurt an der Oder, forming staging nodes where traffic could be reorganized before entering the densely trafficked corridors leading into East Germany. And because the Soviet broad gauge of 1520 millimeters differed from the standard gauge used in Poland and beyond, transshipment complexes at the border were engineered for rapid bogie exchange or cargo transfer, equipped with lifting systems capable of swapping wheel assemblies beneath loaded wagons in compressed time frames, reducing delay that would otherwise extend mobilization timelines. And in addition to physical infrastructure, the rail mobilization system relied on centralized command authority exercised through the Soviet Ministry of Railways, which maintained real-time oversight of traffic flows via dispatch centers connected by secure communications lines, enabling dynamic rerouting if intelligence indicated that certain corridors were compromised or threatened. And this centralized control was mirrored within Allied states whose national rail ministries operated under binding wartime agreements that subordinated civilian schedules to military priority upon activation of mobilization codes, allowing passenger services and commercial freight to be curtailed within hours so that track space could be reserved exclusively for troop and equipment, movement, and exercises such as Zapad 77 and later Zapad 81 incorporated large-scale rail deployments to test these procedures, measuring loading times at garrisons, transit speeds across multiple republics, and unloading efficiency at forward railheads positioned near highway networks feeding the inner German border, with after-action analyses identifying bottlenecks and recommending additional sidings, signaling upgrades or locomotive reassignment to increase throughput margins, and resilience planning extended to engineering units tasked with rapid repair of bomb-damaged track, bridges, and switching yards, equipped with prefabricated rail segments, portable cranes, and bridging kits designed to restore service within hours or days, depending on damage severity, reflecting a doctrinal assumption that NATO air forces would prioritize rail interdiction to slow Pact reinforcement. and thus redundancy, was built not only through parallel routes, but through stockpiled repair material and trained railway troops integrated into mobilization plans. And by the early 1980s, the cumulative effect of these measures was a continental rail grid stretching from the Western Soviet Union through Poland, Czechoslovakia, and East Germany into forward concentration zones, capable under wartime scheduling to deliver multiple divisions per day toward the Central Front, each division requiring dozens of trains and thousands of tons of cargo. And NATO intelligence assessments consistently highlighted this capacity as a decisive factor in early phase balance calculations, noting that the Pact's interior lines and rail density provided an inherent advantage in rapid massing compared to NATO's reliance on maritime reinforcement and more fragmented rail corridors in Western Europe. And this advantage shaped alliance contingency planning, influencing decisions about forward deployed forces, prepositioned equipment, and the timing of reinforcement flights, because the speed at which Warsaw Pact rail mobilization could generate operational mass imposed a narrow window for NATO response. And therefore, throughout the final decade of the Cold War, the rail network remained a central pillar of Pact warfighting capability, translating strategic warning into measurable concentration along Europe's dividing line with a precision rooted in track length, train frequency, axle load tolerance, and synchronized dispatch authority. Beyond the visible main lines that stretched from the Western Soviet Union into Central Europe, the Warsaw Pact rail mobilization system depended on a deeper structural layer of supporting infrastructure that ensured sustained flow once initial echelons began moving, because rapid concentration was not a single surge, but a phased process requiring continuous throughput over several days. And Soviet planners therefore integrated depot positioning, locomotive allocation, fuel provisioning, and maintenance cycles into a unified logistical calculus, calculating not only how many trains could depart per hour, but how long the system could sustain maximum density without mechanical degradation. And to support this requirement, locomotive fleets were organized into priority categories, with heavy freight locomotives assigned mobilization codes that guaranteed immediate availability under activation orders, while reserve locomotives were stored in depots near key junctions to replace units disabled by breakdown or damage, reducing the risk that mechanical failure would create cascading delays across tightly scheduled corridors. And fueling depots for diesel locomotives were expanded along main east-west axes, ensuring that trains could refuel without extended layovers, while electrified segments benefited from dedicated power supply monitoring to maintain consistent voltage under increased draw from intensified traffic. Reflecting the understanding that energy supply was itself a potential bottleneck in sustained mobilization, and marshalling yards were configured to allow parallel loading operations, with reinforced sidings and heavy-duty loading ramps, enabling simultaneous embarkation of multiple battalions, thereby compressing divisional loading time to meet doctrinal benchmarks that often targeted completion within 36 hours of mobilization order, and unloading facilities near forward areas were similarly engineered for rapid transition from rail to road, with multiple detrainment points distributed to reduce vulnerability to air attack and prevent congestion at a single node. And because Soviet operational doctrine anticipated that NATO would attempt to disrupt rail bridges and choke points using tactical aircraft and possibly precision munitions, engineer units were integrated directly into mobilization columns, traveling with bridging equipment capable of constructing temporary spans across damaged river crossings, while track repair battalions trained to replace rails, sleepers, and switches under field conditions, often rehearsing these procedures during large-scale exercises in which segments were deliberately taken out of service to test restoration timelines. and signaling modernization programs in the late 1970s introduced automated block control and centralized traffic management in critical sectors, reducing reliance on manual dispatch and increasing permissible train frequency per track by tightening safe headway intervals, thereby raising theoretical maximum throughput in trains per day, a metric closely monitored by Soviet planners who sought to ensure that the rail grid could deliver follow-on armies without exceeding saturation thresholds that would produce gridlock, and intelligence gathered by NATO throughout the 1980s repeatedly underscored the density of packed rail infrastructure in East Germany, where short distances between garrisons and the inner German border meant that units could be loaded, transported, and unloaded within compressed timeframes, measured in hours rather than days, reinforcing Western concern that a coordinated mobilization might achieve operational surprise, even if strategic warning indicators were detected. And this concern was compounded by the Pact's ability to conceal preparatory rail movements within the volume of routine freight traffic during peacetime, because civilian and military use of shared lines allowed partial mobilization steps to be masked within normal activity until full activation codes were issued, at which point civilian schedules would be curtailed and priority corridors reserved exclusively for military trains, a transition rehearsed in periodic readiness drills that measured the time required to clear passenger services and allocate track space to mobilization echelons. And by the mid-1980s, the rail network supporting the Western theater of military operations had achieved a level of integration in which infrastructure, rolling stock, dispatch authority, and engineer support formed, a single operational system designed to translate mass into motion with minimal delay, shaping NATO's defensive planning by compressing the expected timeline between political crisis and large-scale force concentration. And thus, throughout the final decade of the Cold War, the Warsaw Pact rail grid remained one of the most critical enablers of its conventional warfighting doctrine, a logistical architecture measured in kilometers of track, locomotive horsepower, and train frequency, engineered to ensure that divisions stationed deep within Soviet territory could appear at the threshold of Western Europe with a speed calibrated by decades of systematic investment and rehearsal. The effectiveness of the Warsaw Pact rail mobilization design was inseparable from the Pact's echeloned war concept, because Soviet operational art assumed that conflict in Central Europe would unfold in rapid phases, requiring the continuous introduction of fresh formations behind forward assault armies. And this required rail corridors not merely capable of delivering an initial surge, but able to sustain layered reinforcement over a period measured in days and weeks. And accordingly, Soviet planners structured traffic flow into priority waves, assigning first echelon armies immediate track access along the shortest and most direct routes into East Germany, while second and third echelon formations, departing from interior military districts, were sequenced into subsequent windows, calculated against projected unloading completion times at forward railheads, ensuring that detrainment sites would not become saturated before preceding units had cleared the area. And these sequencing models incorporated measurable unloading rates per ramp, often estimating how many tanks or armored vehicles could be offloaded per hour based on ramp width, crane capacity, and crew strength. And by multiplying these rates across multiple sidings at a given railhead, planners derived maximum divisional turnover times, which then fed back into upstream dispatch schedules, creating a closed-loop system in which arrival timing, unloading throughput, and onward road movement were mathematically synchronized. And because NATO doctrine emphasized deep interdiction by tactical air forces, the Warsaw Pact invested in dispersal strategies that distributed unloading across numerous smaller railheads rather than concentrating at a few major terminals, thereby complicating targeting and reducing the operational impact of any single strike. And redundancy extended to bridge construction, where parallel crossings were maintained where possible, and engineering reconnaissance identified alternate routes capable of absorbing diverted traffic if primary spans were disabled. And throughout the 1980s, Soviet and Allied railway troops conducted field exercises simulating damaged infrastructure, practicing rapid emplacement of temporary track panels and portable signaling equipment to restore limited service. Within hours, reflecting the doctrinal expectation that even under sustained air attack, rail flow must be preserved to maintain offensive momentum. And NATO intelligence reporting during this period repeatedly highlighted the density of rail lines feeding the German Democratic Republic, noting that short internal distances allowed East German-based divisions to mobilize onto rail and reach concentration zones near the inner German border within a single operational day, while reinforcements from Poland could follow within similarly compressed timelines. And this proximity created a strategic asymmetry because NATO reinforcements from North America would require transatlantic transit before rail distribution in Western Europe could begin, effectively granting the Pact a temporal advantage in initial massing. And this advantage was amplified by centralized command authority within the Soviet Ministry of Railways, which exercised unified dispatch control across republic boundaries, enabling rapid reallocation of locomotives and rolling stock without the intergovernmental negotiation that characterized Western European rail systems. And by integrating rail mobilization planning directly into general staff war games and operational planning cycles, the Warsaw Pact ensured that infrastructure investment decisions, including additional double tracking and signaling modernization, were aligned with projected force structure growth and doctrinal evolution. And thus, as new tank models increased vehicle weight, flat car axle ratings were adjusted, and bridge reinforcement programs implemented to maintain safe load margins, preventing structural constraints from limiting future deployment speed. And by the late 1980s, the cumulative system represented a continental-scale logistical framework extending from the Urals to the Elbe, engineered to convert mobilization orders into physical movement with precision measured in trains per day, tons per corridor, and hours per divisional transfer, shaping NATO's defensive posture by compressing warning time and reinforcing the perception that any delay in Western response could permit the Pact to achieve overwhelming concentration at the decisive point, thereby embedding rail capacity into the strategic balance that defined the Cold War's central front. As political tensions intensified during periods such as the Euro missile crisis in the early 1980s, Western intelligence agencies devoted sustained analytical effort to quantifying the Warsaw Pact's rail mobilization capacity because accurate estimates of trains per day, divisional lift requirements, and corridor saturation thresholds were essential for modeling how quickly Pact forces could mass against NATO's central front. And satellite imagery, signals intelligence, and human reporting were combined to map yard expansions, new sidings, bridge reinforcements, and locomotive concentrations, producing assessments that often calculated how many full divisions could be transported from interior Soviet military districts to forward areas within the first week of conflict, with estimates frequently citing dozens of trains required per tank or motor rifle division and hundreds of trains per combined arms army. And these calculations highlighted the degree to which the Pact's rail system was structured around mobilization, first principles rather than purely commercial efficiency, because double tracking, bypass lines, and reinforced crossings were disproportionately concentrated along east-west axes aligned with offensive planning. And NATO analysts noted that the density of railheads in East Germany reduced the distance between unloading points and potential forward assembly areas to less than 100 kilometers in many sectors, meaning that units could transition from rail to road and approach the inner German border within hours of detrainment, compressing the timeline between strategic decision and tactical engagement. And this compression shaped NATO contingency planning, reinforcing the need for forward-deployed forces and pre-positioned equipment capable of immediate response without waiting for transatlantic reinforcement. And within the Warsaw Pact itself, rail mobilization procedures were refined through periodic inspections in which readiness levels of locomotives, availability of flat cars rated for heavy armor, and condition of signaling systems were evaluated against mobilization benchmarks, with deficiencies triggering targeted infrastructure investment under centrally directed programs. And because sustained high-density traffic placed significant stress on track, sleepers, and ballast, maintenance regimens were intensified along designated mobilization corridors, including scheduled replacement of worn rails and reinforcement of embankments in sectors vulnerable to subsidence, ensuring that wartime surge would not encounter structural degradation accumulated during peacetime freight. Operations and contingency planning also addressed winter conditions, with snow removal equipment pre-positioned and cold weather operating procedures codified to prevent ice accumulation from slowing train frequency, recognizing that climate could otherwise erode the very speed advantage the system was designed to secure. And as reforms unfolded in Eastern Europe after 1989, including the political transformations in Poland, Czechoslovakia, and East Germany, the rail mobilization network remained physically intact even as the strategic context shifted, a reminder that decades of investment in track, yards, and rolling stock had created a durable logistical skeleton capable of supporting mass movement, irrespective of immediate political alignment. And when the Warsaw Pact formally dissolved in 1991, the infrastructure that had once been calibrated for rapid offensive concentration did not vanish. But its strategic purpose was fundamentally altered. Yet throughout the Cold War, its existence had shaped the balance of power in Europe by providing the Pact with a measurable capacity to translate mobilization orders into concentrated force within compressed timelines. A capacity rooted in kilometers of double-tracked main line, reinforced bridges spanning major rivers, locomotive fleets maintained at priority readiness, and dispatch systems engineered for centralized control. And in that capacity, the rail network functioned as the backbone of Warsaw Pact war planning, converting strategic doctrine into scheduled motion and embedding speed as a decisive variable in the confrontation that defined Europe's divided decades. When assessed across the entirety of the Cold War, the Warsaw Pact rail mobilization network represented a structural embodiment of Soviet operational doctrine, translating theoretical concepts of echelon defense and rapid concentration into a continent-spanning transport grid calibrated for speed, density, and resilience. And from the initial post-war reinforcement of trunk lines in the Western Soviet Union through the systematic double-tracking, bridge strengthening, yard expansion, and signaling modernization undertaken in Poland, Czechoslovakia, and East Germany, the system was engineered with a singular objective: to ensure that divisions stationed hundreds or even thousands of kilometers from the central front could be loaded, dispatched, and unloaded within timelines measured in days rather than weeks. And this objective was operationalized through detailed mobilization timetables, assigning specific corridors to specific formations, allocating trains per division, and synchronizing arrival windows with unloading throughput at forward railheads, thereby creating a closed logistical loop in which departure frequency, transit duration, and detrainment capacity were mathematically aligned, and redundancy was embedded at every level, from parallel east-west corridors capable of absorbing rerouted traffic to railway troops, equipped for rapid repair of bomb-damaged segments, reflecting the doctrinal expectation that NATO would attempt early interdiction, yet acknowledging that momentum had to be preserved despite disruption. And locomotive fleets were categorized for priority mobilization use. Fuel depots and maintenance facilities were positioned to sustain continuous traffic, and centralized dispatch authority under the Soviet Ministry of Railways ensured that civilian services could be curtailed immediately upon activation, converting commercial infrastructure into an exclusive military conduit within hours. And NATO intelligence consistently assessed that this integration of infrastructure and doctrine granted the pact a temporal advantage in initial massing, particularly given the proximity of East German railheads to the inner German border, and the interior lines connecting Soviet Western military districts to Central Europe, shaping Western planning assumptions about warning time and reinforcement requirements. And as new armored systems increased vehicle weight and doctrinal emphasis shifted toward deeper operational exploitation in the late 1970s and 1980s, flat car ratings, bridge capacities, and signaling systems were upgraded accordingly, demonstrating that the rail grid evolved in parallel with force structure rather than remaining static. And by the end of the 1980s, the cumulative network extended from the Urals to the Elbe through thousands of kilometers of main line, capable under mobilization scheduling of dispatching dozens of trains per corridor per day, each train carrying tanks, artillery, ammunition, fuel, and support equipment essential to sustained offensive operations. And although the political transformation of Eastern Europe and the dissolution of the Warsaw Pact in 1991 fundamentally altered the strategic environment for which the system had been designed, the infrastructure itself stood as evidence of decades of preparation, rooted in measurable capacity, rather than rhetorical posture. And throughout the Cold War, this rail mobilization architecture functioned as the backbone of Pact conventional war planning, converting strategic intent into scheduled motion and embedding speed, mass, and coordination into the logistical foundations of Europe's most heavily militarized frontier.